Hi everyone, my name is Timing Yang, and today I'll be presenting my work on the control system design for an ideal binary distillation column. This presentation will cover the modeling, transfer function, and control system design using MATLAB, handling multiple set points and disturbance, and finally tuning of controllers. We begin with the modeling of the ideal binary distillation column. First, we make assumptions including constant molar flow rates of vapor and liquid through the stripping and rectifying sections, perfect insulation with no heat loss to the surroundings, constant liquid hold-ups on each tray, condenser, and reboiler, negligible vapor hold-up throughout the system. The mass balance equation around the condenser and reflux drum, top tray, next to top tray, end tray, feed tray, first tray, and reboiler and column base were derived. These equations are essential for developing the transfer functions. Also, we calculate the relative volatility alpha, which is 1.3922. Next, we move to the transfer functions. The overall transfer function relates the top and bottom product compositions to the manipulated variables, which are the reflux ratio and the reboiler steam flow rate. The four transfer functions, including condenser and reflux drum, overall column and reboiler, overall column and condenser, and reboiler, were derived as follows. Finally, we will get an overall transfer function in matrix form. The control system design for the distillation column was performed for both servo and regulatory changes using manual and toolbox controllers. First, let's see the manual controller. The block diagram of the control system is shown here. First, let's see the servo control using manual controller. Servo control, also known as set point change, refers to the process where the primary objective is to make the system output follow a desired set point as close as possible. For the servo change, the set point for the composition of distillate XD and the composition of bottom XB was specified, and all disturbance was set to 0. Also, we set our Kp to 100, and the response using P, Pi, and PID controller were analyzed. From the result, the PID controller was found to be the most effective with minimal oscillations, no overshoot for XD, lower overshoot for XB, shorter settling times, and reached the steady state set point value faster than P and PI controller, and 0 offset. Next, we move to the regulatory control using manual controller. Regulatory control, also known as load control, is concerned with maintaining the process variable at a constant set point despite disturbance or change in the load. For regulatory changes, disturbance were introduced, and the system ability to maintain the desired set point was tested. We set the load at 50. Again, the PID controller demonstrates the best performance with the least oscillations and the quickest response to the set point changes. Now, we move to the toolbox controller. The block diagram of the control system is shown here. For servo change, we did the same thing like manual controller. We set our Kp to 100 and disturbance to 0, and the response using P, Pi, and PID controller were analyzed. Result shows the PID controller has the best performance with the least oscillation and the quickest response to the set point changes. For regulatory changes, same thing like we did for manual controller, we set the loads at 50 and we analyze the response using P, Pi, and PID controllers. Again, the PID controller is the best controller as it demonstrates the best performance with the least oscillations and the quickest response to the set point changes. Let's discuss handling multiple set points and disturbance. In real-world application, a distillation column often needs to maintain multiple set points for different product compositions while dealing with various disturbances. The block diagram of the control system with multiple set points and disturbance is shown here. For servo change, we set Kp to 100 and we introduce multiple set points at different step time 1, 3, 5, and the response using P, Pi, and PID controller were analyzed. From the result, we found that the PID controller is still the best controller as both responses for XD and XB have no oscillation effect, no overshoot, shorter settling time, and also zero offset. For rotatory change, we set the multiple loads at 50 at set time 1 and 3, and we analyze the responses using P, Pi, and PID controllers. Again and again, the PID controller demonstrates the best performance with no oscillations and the quickest response to the set point. Now, let's discuss the tuning of controllers using two widely recognized methods, Ziegler-Nichols and Cohen-Cohn. For Ziegler-Nichols method, first set the I integral and D derivative gains to 0, turn on the P proportional mode and increase controller gain Kc until the system reaches the ultimate gain Ku, at which the output of the loop starts to oscillate consistently. The examples are shown below. And measure the period of oscillation Pu. Finally, use the Ziegler-Nichols tuning table to calculate the P, I, and D values. Here shows the formula and the calculated values of ZL method for P, I, and D control settings. This is the block diagram for the control system using ZN tuning method. After tuning, we found that the best controller is still the PID controller, as both responses for XD and XB has the lowest number of oscillation, lower overshooting, shorter settling time, and reach the steady state set point value faster than P and PI controllers and have zero offset. For Cohen-Cohn method, we perform an open loop test to determine the process reaction curve. We'll draw a straight line tangent to the curve at the point of inflection to determine TD, which is the intersection of tangent line with time axis, and BU, which is the ultimate value of B at large T. From the value obtained, we can find T and Kp. Finally, use the CC tuning formulas to determine the PID parameters. Here shows the formula and the calculated value of CC method for P, I, and D control settings. This is the block diagram for the control system using CC method, and we can see it is an open loop system. After tuning, we analyze the responses using P, Pi, and PID controllers. And from the result, we found that the PID controller is the best controller with no oscillations, no overshoot, and quickest response to the set point. We will do the comparison between the two tuning methods, Ziegler-Nichols and Cohen-Cohn. From the previous result, we found that Cohen-Cohn method is a better method to be used for tuning compared to the Ziegler-Nichols method. This is because the response curve for Cohen-Cohn method has no oscillatory effect and overshooting value. Although the settling time for Cohen-Cohn method seems longer, but the response for both XD and XB have low overshooting value and even zero offset. Unlike the response for XD and XB in Ziegler methods, there is large overshooting value. And these are the reasons why Cohen-Cohn method is a better tuning method. Thank you for listening.